Yeah, we be doing weekly stuff. They're on the YouTube. You can check the events channel, and there's a link to the YouTube. Of course. I'll begin in like a minute. Yeah, I need to get on to I get on that. I need to record myself giving the lecture. I just have been pretty lazy. But I'll do that. If not tonight, then tomorrow. Okay. Yeah, so for the abstract algebra, I don't think we didn't cover enough for me to give a problem set. I will release the notes, and you'll get a problem set next week. Oh, well, this week. Okay. I'm gonna begin now. Okay. So, this week we're going to be talking about first order logic. First order logic is probably something you guys have at least heard about. But we're going to the exact formalization of that is of first order logic is not entirely what you would expect. So let's start with that. We're going to start with something that seems a little disconnected, but it'll all come together. So let's talk about a few definitions from algebra. So one, oh, that's too big. A group is a math structure, right, which consists of a set and an operation, right? That's what a group is, which satisfies some axioms. Two. Yeah, we can talk. We can talk about that later. I think. At the end of the lecture, or in private. A field is also a math structure. F plus times 0, 1, which also satisfies some axioms, right? And to give a non-algebraic example, 3, a poset, a partially ordered set, is a mathematical structure which consists of a set and some binary relation on the set, which satisfies some axioms. So in general, what we kind of see here is a math structure is an object of the form a dot dot dot. So we have a set and then some constants, right? We have constants from fields and relations from partially ordered set, right? We have a relation here and operations, right? We have additions, multiplication, and whatnot. And so that sort of seems to be the sort of pattern with mathematical structure. And well, that's the first part of first order logic that we're going to talk about is our mathematical structures. The second part that we'll talk about is what this means, which satisfies some axioms. But let's focus on mathematical structures for now. So let's try to formalize this. Right? So what we're going to formalize first, right, which is the least clear part of this definition, is what this dot 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 is. So definition, an extra logical, I'm going to put that in parentheses, signature is is an object sigma which has 3 types of symbols. Right, so it's an object. You can think of it as a set of symbols. Each of those symbols is one of 3 types. Sorry, one sec. Let me. One of 3 types. So one, you have constant symbols. So these I'm going to be writing like C in sigma. And whenever I write C, I'm not going to specify that it's a constant. You'll know because I'm calling it C. 2 function symbols, F in sigma, and finally relation symbols, which are R in sigma. And so a signature is a set of objects, of symbols, and it's not enough for it to be a set of 3 types of distinct symbols. We need a little bit more information. And for every function symbol or relation symbol S, an arity, which will denote AR of S, which is in n greater than 0. Yes, a constant can be thought of as a function without an argument, though I'm going to consider it as its own independent thing for now. When we get to proofs later on, we're kind of just going to ignore the arguments for constants because they're subsumed by the arguments for functions. And then I would have to like split into cases here, like the arity of S is in n greater than or equal to 0 if S is a function symbol, or greater than 0 if it's a relation symbol, or consider relation symbols that don't take arguments. But yes, you can consider constants as zero-ary functions. Okay. Yeah. Okay. So for example, we can look at the signature of fields / rings, right? They're over the same signature, which is plus times 0, 1, right? Yes. So you can have a signature that doesn't have. You can have an empty signature too. It just if it does it has. You can think of it as a triplet, where it has you have a triplet of C of constant symbols, F of function symbols, and R of relation symbols, and maybe a quadruplet and AR, right? And that's sort of what if you want to formalize what a signature is. But these can be empty. Okay, so the signature of fields and rings, right, for example, doesn't have a relation symbol. It does have 2 binary functions, right? So these are function symbols with an arity of 2. and these are constants. The signature of posets only has a single relation with an arity of 2. Okay. Yeah. And we call a signature algebraic if it does not have any relation symbols. So this, for example, is an algebraic signature. Okay, so now that we've defined what a signature is, let's define now what a mathematical structure is. Let sigma be an extralogical signature. A sigma structure is an object A which consists of 1. So, right, if we look again at our examples at the beginning, a mathematical structure, all of them are over some set. Equality we'll get to. Are over some set. So, right, every sigma structure has a domain, which we denote dom of A, or sometimes I'll just also write A for the domain, right? We can sort of abuse notation here and write the symbol for the structure for its domain. Right? When I'm talking about G as a group, I write like I can say G is a group, so it's a mathematical structure. So what I mean here is G is equal to some G with a circle, and then I can sort of conflate these two. There are non-set-like structures, but we don't study them. Right? This is not an exhaustive study of everything in mathematics. Yeah. So it's a domain. For every constant symbol in sigma, an element, so we call an element C of A. So C superscript A in A, well, in the domain of A. 3, for every function symbol in sigma, a function f of A, which is from the domain of A to the power of the arity of f to the domain of A. So for example, if f has an arity of 2, then f of A would be from the domain of A times the domain of A to the domain of A. That's the. I mean, it depends on what exactly you mean by model. Like, I'm pretty sure you can't fully talk about category theory in the context of first order logic, and you can't talk about second order logic in the context of first order logic, right? Or like to an extent, you can't talk about the theory of natural numbers in first order logic up to isomorphism, because anything that satisfies there exists models of the theory of natural numbers which are non-isomorphic to the natural numbers. So that's going to be a result that we get to, but not everything can be modeled so well with first order logic, but that's in and of itself a study. Yeah. Well, okay. I think we're getting off on a little bit of a tangent, and questions that I can't fully answer off the top of my head. But we'll be able to answer those questions once we understand what first order logic is. Okay. For every relation symbol in sigma of relation, which is R of A, which is a subset of the domain of A to the power of the arity of R. These three things are called interpretations of the symbols in the signature. So, for example, let's take the signature, like the signature of fields. Let's call that sigma sub f, which has plus, times, 0, and 1. Now, these are all symbols, and I can define a sigma sub f structure, which let's call it R, which has a domain of R, the real numbers, plus, which is interpreted canonically, multiplication, which is also interpreted canonically, 0, which is interpreted canonically, and 1, which is interpreted canonically. There's nothing that made me interpret it the way that I interpret it. I read like the way that I didn't have to interpret it canonically. I could have interpreted it as R with plus, which just sends x and y to 0, times, which sends x and y to 1, 0 of R, which say I can equal the square root of 2, and 1 of R, which equals the square root of pi to the power of e. Right? There's nothing that's making me make sure that here R prime, R prime, R prime, R prime. There's nothing that's making me interpret these functions and these constant symbols and these relation symbols as one might intend. Yeah, but it's nicer for me to write in the middle of the screen, because otherwise my hand slips off my desk. Okay. Okay. So, okay. So up until here, right, we've defined what a sigma structure is. Now, what's a common thing that every structure has? Well, not every structure, but when we're talking about a theory of things, right? When we're talking about groups, or we're talking about fields, or we're talking about graphs, we can talk about subgraphs and subfields and subgroups. So let's now define what it means for something to be, here, I'll try to write a little lower. So let's try to define what a substructure is. Let sigma be a signature, a sigma structure, and B a subset of A. So this is a subset of the domain of A. Right? Because I said that I was going to conflate the two. And it's a little more easy to distinguish between them when I'm writing them in my lecture notes, because I use different fonts, but it doesn't really matter. Okay, so a sigma structure and B a subset of A, such that 1, for every constant, C of A is in B. So every constant in A is also in B. Well, every constant, the interpretation of every constant is in B. And 2, for every F in sigma and a vector of elements in B. So write a vector, I'm going to write, here again, I'm going to abuse notation, I'm going to write a vector of elements in B instead of a vector of elements in B to the power of n. Just for my ease. It shouldn't be so confusing. I'm writing a bar over the A. For every function symbol and every vector of elements in B, the image of this vector is also in B. So it's closed under constants, and it's closed under taking function images of the functions in the signature. Then we can naturally define a sigma structure on B by, so one, C of B, the interpretation of C under B is just going to be the same interpretation of C under A, right? Because it's already in B. 2, f of B is just going to equal the f of A, the interpretation of A, restricted to B to the power of n to B, right? Because it's closed under taking these functions. And 3, right? R of B is just going to equal R of A restricted to B, which is just R of A intersect with B to the power of n. So for example, let's take a look at the signature circle for groups, right? And then we have we have the structure Z, right, of the integers. That is not a good look. I'll just write Z normally, which is addition, right? We interpret this circle operation as addition, and we can look at substructures of this. And so we know from group theory that some substructures of this group are of the form n z, which are equal to n times z with addition. But here, it's important to note that the signature here matters, because another substructure of z is n, which is just the natural numbers with addition. Now, why is this a substructure? Because addition, n is closed under addition. If a and b are in n, then a plus b is a natural number as well. So when you're talking about substructures, it's important to remember that not everything, that you have to be careful about your signature as well. And this will kind of show up. There's this idea of definability and whatnot, but that's still, we'll get to that later, why this happens later. That this is like very interesting. This is interesting. Like I can also add, I can add 0 to our signature, right? 0, z plus and 0, and still n greater than or equal to 0 is still a substructure. But we do alleviate all these issues when I add plus, minus, and 0 to the signature. No, that's what I'm saying. N is not a subgroup of Z, but it is a substructure of Z under a particular signature. So if I finally take if I take this to be my signature, all subgroups, all substructures of this structure, substructures are groups. So what I'm trying to say here is that the signature that you're working under is important. Obviously, just because I can define other functions with that signature, right? I can define 0, right? I can define 0, and I can define inverses using addition, right? I can say that that minus a is just the unique x, such that, so x equals minus a if and only if for all, if and only if x plus a is equal to 0, right? And this uniquely defines minus a, but that doesn't mean that everything that carries over, right? Your signature, just because you can define other things in other things beyond your signature, doesn't mean that everything that you want to talk about carries over. Okay, I spent a long time on that. I should not have. Sorry if I confuse people. Um, okay, another similar definition to a substructure is a reduct. So let sigma naught be a subsignature of sigma. Sigma naught be a substructure of sigma, and a sigma structure. Then the sigma naught reduct of A is the sigma naught structure obtained by interpreting S in sigma naught by S of A. And we denote this by A restricted to sigma naught. So this is like a weird definition. Pretty much what I'm saying is that if I have a subsignature, I can just define the reduct of this to forget about everything that's not in the signature. Right? So if I have, let's say, I have the signature of fields, so plus, times, 0, and 1, then I can forget about everything else. So, and let's say R is a field. I can forget about everything else. So this is sigma, and this is sigma naught. I can forget everything about everything other than plus, and now I have R under plus. And this is the reduct of the field R. It gives me the group R. No, that wasn't what I meant. What I meant was, that was one of the points that I meant previously. What I'm saying here um, is that you could define, just because you can define subtraction or inverses using addition, but that doesn't mean that just taking it away from the signature gives you all the same results as you would have with it in the signature. Okay. So a reduct basically just means that you interpret everything the same, but maybe you're losing a few symbols. Could be. A reduction. I mean, it's not short, it's a different word, but they probably both, reduction comes from. I'm not an English expert. My English is actually quite shit. Okay. Okay, so now we have this this notion of structures, and what do we love to study about structures? We love to study about maps which preserve the structure, right? That's another word for homomorphisms. So let us define what a homomorphism is. Let A and B be sigma structures. H is a map from A to B. So, right, it's a map between A and B. The domain of A and the domain of B is a homomorphism if, firstly, so one, for all F in the signature, H of F of A is equal F of B of H of A. Okay, this is a little, maybe a little confusing, but if I write it out, and H of A is equal to HA1 through HAN. So if I write this out explicitly, let's say with an example, let's say F is equal to addition. What I'm saying here is H of A plus B is equal to H of A plus H of B. Yes, exactly. If you reduce your signature, your proofs may not carry over. You could think of it that way, yeah, sure. Okay. So that takes care of functions. Constants are pretty easy, right? H of C of A is equal to C of B. So it maps one constant to the other. And free, relations are where it gets a little weird. R of A implies R B of H of A. So these are the three axioms, I guess you could say, or three rules that a homomorphism must follow. Is that it preserves constants, it preserves functions, and to an extent it preserves relations. Now, what's this definition is actually not really useful, and we never do use it. Instead, what we're going to define is a strong homomorphism is a homomorphism where 3 is replaced by so RBH of A if and only if there exists some B such that H of A is equal to H of B and RA of B. Okay, so this is a little lengthy, and basically what it says is that if firstly it's an if and only if now. It says that RBH of A, if and only if there's some B whose image is the same as A's, and it satisfies the relation. So obviously a strong homomorphism is going to be a weak homomorphism, because if RA of A, then this certainly holds. But the idea being that this is too weak, and saying RA of A if and only if RBH of A, this is too strong. So we take something in the middle. Okay. And an injective strong homomorphism is an embedding. And a surjective embedding is, of course, an isomorphism. Okay, so let's quickly go over some examples. Everything here. Some points to make. So if an embedding, if this is an embedding, if H is an embedding, then this can be simplified to simply RBH of A, if and only if RA of A, right? We get what we had before, because it's an embedding, so H of A is equal to H of B if and only if A is equal to B. So what we had before, what I said was too strong. For an embedding, it doesn't really matter. It's the same thing. And for a surjective homomorphism, you can simplify this further. What is it? It's something like RB of B, if and only if, or RB is all the B such that, or is it here? H of A such that RA of A. Right? If H is surjective, then you can explicitly find what R of B is. It's all the H of A's such that A satisfies the relation. Yeah, sure. This is true in general. Take something that's not of two non-homomorphisms. Oh yeah, you can still take something that maps like everything to zero except one number and take something that maps that number to zero. You compose them together, you get the zero homomorphism. Okay. Now, if I recall correctly, and this is not an important point, but the composition of strong homomorphisms here is not a strong homomorphism. The composition of surjective strong homomorphisms is a strong homomorphism. The first one needs to be surjective. But then the composition of embeddings is an embedding, the compositions of the isomorphisms is an isomorphism, and we don't actually care that much about homomorphisms. We care mostly about isomorphisms and embeddings. Yeah. Okay. Notice that if I is an isomorphism, then the inverse of I is also an isomorphism. Everything that you think holds for isomorphisms does hold for isomorphisms, pretty much. Like all the basic facts, obviously. If H from A to B, for example, if A from H to A to B is a homomorphism, then H of A is a substructure of B. That's also true. You could do that. Okay. Okay. Now let's get to a congruence. So, oh no. Okay. A congruence on a sigma structure. On a sigma structure A is an equivalence relation theta such that for all f in sigma and a b in A, if A theta B, then f of A theta f of B. What this means, right, is AI theta BI for all I for I equals 1 through n. Yeah. Okay, so that's a congruence. It's pretty much just an equivalence relation that preserves functions. Okay, and the congruence. Now, obviously, the equivalent of a homomorphism or the analog of a homomorphism in group theory or field theory or ring theory, are homomorphisms or group homomorphisms, ring homomorphisms, and whatnot. And the analog of a congruence in group theory is normal groups, and in ring theory it's ideals. And the reason for that is because actually every congruence on a group forms a normal subgroup. So I'll show one direction. Suppose n is a normal subgroup of G, then A theta B defined to be A B minus 1 in N is a is a congruence. And I'll leave this to verify yourselves. And this is going to be something on the problem set as well. It'll be interesting. Okay. Now, the reason why this is the analog of a normal subgroup is because what can you do with a normal subgroup is you can quotient by it. And similarly, you can quotient by a congruence. So if theta is a congruence on A, then B equal to A over theta, the quotient structure is defined as follows. So one, the domain of B is obviously just going to be the quotient set, right? It's the domain of A partitioned by theta. Yes. C of C of A over theta is just going to be equal to the congruence class of CA over theta, right? I'm going to write A over theta for the congruence class of theta, of A, sorry. F of A over theta of a vector of congruence classes is just going to be F of A over theta, sorry, F of A, F superscript A, the interpretation of F of A, and then that's equivalence class. Now, why is this well defined? Well defined. This is well defined, right? Because if A theta B, right, meaning A over theta is equal to B over theta, then F of A theta F of B, meaning F of A over theta is equal to F of B over theta. Right, so this is well defined, precisely because of this implication. And for finally, R of A over theta of A over theta, if and only if there exists a B in A over theta such that RA of B. Okay, so a quotient, an equivalence class or a congruence class, sorry, satisfies a relation if and only if one of its elements satisfied the original relation in A. Okay. Now, an important example of a congruence, right, in any study is going to be kernels, right? So if H from A to B is a homomorphism, then its kernel is the congruence A per H B if and only if H of A is equal to H of B. And you can verify yourselves that this is a congruence. It's literally because of the definition of homomorphisms that you can sort of commute with F. And so this is a congruence, and so then you can look at A over the kernel of H. And if we remember, right, if H is surjective, for groups we got that this was isomorphic to B. They're not redundant. That's not nice. They're just congruent. Okay. So in groups, we get this, right? This is the first isomorphism theorem, right? So the question is does this hold in for structures as well? And the answer is yes. That's claim our first theorem. Oh, okay. So in the problem set, I wrote that we proved this. We did not prove this. We're not going to prove this. You prove this in the problem set. Okay. 1, let A be a sigma structure, and and theta a congruence. Then pi, pi from A to A over theta, right? Maybe a better one would have been rho. This is the quotient, the quotient homomorphism which maps A to its congruence class, is a strong homomorphism. Right. So what this tells us, right, is that this canonical homomorphism that we're all used to, right, in group theory, right, we should all be very used to it. It's always a homomorphism for any structure, and any congruence. 2, if H from A to B is a strong homomorphism, then H tilde from A over theta from the quotient structure to B, to H of A, sorry, H of A is a defined by H of A over theta is equal to H of A is an isomorphism. And H is equal to H tilde composed with pi. So what this tells us, right, is literally this is just the first isomorphism theorem for groups translated to structures. There's nothing special about this theorem. I mean, other than the fact that it's a great theorem, there's nothing special about this theorem. And what it does give us is it gives us the power to generalize the classic meme. Right, we have A, H tilde, or I guess it's phi in the sticker, but to cur H, and that's downward to B, and this is H, and this is pi. No, this is pi. Sorry, I think I wrote it wrong in this. Yeah, I did. This is pi, and this is H tilde. So I wrote it wrong in my notes. I'm gonna have to fix that. But this is the generalized sort of commutative diagram. Yes, that. And this works for any structure. It's great. It's very I think it's very nice how you can you have all of this mix of this. I think this really shows that all of these definitions are very natural, because while there were a lot of definitions, they all kind of make sense. And this is one example of why they make sense. Okay, so I've gone along on a long, not a tangent, this is very important, but a very long discussion about first order structures or mathematical structures. Now it's time to actually talk about what first order logic is, right? That's the whole point of this lecture that we're already halfway through. Speaking of, do I have enough time? Yeah, okay. So, okay. First we have to talk about the syntax of first order logic. So, we can't remember in propositional logic I had a set of propositional variables, and from that I could immediately go to defining what propositional formulas are. For first order logic I can't do that. For first order logic we have this intermediate sort of object called a term that we will need, that I'll define right now. So let sigma be a signature. Then a sigma term is defined recursively as one for C in sigma, C is a term. So I'm going to write, that's going to be our notation for the set of sigma terms, is going to be T sub sigma. Yeah, so that's another first commutative diagram for the first isomorphism theorem. It says, so the first arrow means that it's surjective, the second arrow means it's isomorphism, and then the third arrow is an embedding, and all of those composed together gives you phi. But that's not important. Okay. Oh, and we have a global list of variables. This time our list of variables doesn't change. It's v1, v2, v3, and so on. It's only countable. Okay. And 2, every x in var, x is also a term. Oh, shoot, sorry. X is also a term. And 3, finally, if t1 through tn are terms and f is in sigma, then ft1 tn is a term as well. So for example, if our signature is plus times 0, 1, then v1 plus v2 times 1 plus 1 is a term. Right, obviously you have to turn this into prefix notation, but it doesn't matter here, right? By we all, I mean I did, we all agreed that infix notation doesn't really matter, right? Like it works, we can use infix notation. Okay. Obviously there's this notion of term induction, right? If I prove it for constants, I prove it for variables, I assume it for t1 through tn, and then I prove it for f of t1 through f t1, t2, blah, 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 tn, then it holds for all terms. So there is a concept of term induction. There's also, because terms are pretty much the same thing as, like the structure of terms is pretty much the same thing as the structure of propositional formulas, we also have unique term reconstruction. Everything that we're going to have, we have to have unique X reconstruction. So here we have the unique term reconstruction property, we're going to have the unique formula reconstruction property, and so on. And because of the unique term reconstruction property, we can define the variables in, so postfix notation is for losers. We can define the variables in a term recursively as follows. So the variable of a constant is, there are no variables. The variable of a term which is just a variable is just that variable. And the variable of f of t1 blah 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 tn is a union of the variables in ti from I equals 1 through n. Okay, again, we don't really need to use, like I said before when we were talking about propositional logic, we don't really need to use recursion here. It's just pretty handy to do so. Okay, so now that we finally defined terms, we can finally define what first order formulas are. So let sigma be a signature, then sigma formulas, then the set of sigma formulas, L sub sigma, is defined by 1, if T and S are two terms, two sigma terms, then T equals S is a formula. 2, if R is a relation symbol in sigma, and T1 through Tn are terms, then RT1 Tn is a formula. 3, if alpha, beta are formulas, and, oh, sorry, that's not F, we're using an L, are formulas, and X is a variable, then alpha and beta, the negation of alpha, and for all X alpha are all formulas. Okay, so we can have formulas, for example, also I can conflate L sub sigma with sigma, because right, there's a one-to-one correspondence between all the set of first order, like sets of first order formulas and first order signatures. So instead of sigma structures, respectively, terms, etc., we write L structures, etc. This is just because this is very common in literature. Instead of talking about the signature, you talk about the language. So you're not going to go really see people going around saying stigma for stigma structures. You'll see them talking about L structures. Okay. Now, these two things, these two types of formulas are called atomic or prime formulas. Yeah. So these are called atomic and prime formulas. So for example, I can write for all x equals, let's just take whatever constants and symbols I write, just assume those are in the signature. X equals 1 plus 2, and for all y is equal to x. So this is a formula. It doesn't really make sense, but it's a formula. No, so equals, okay. Equals, so you can talk about identityless, what's it called? Identityless theories and logics, and those don't have the equal sign as a primitive part of the logic. But you lose strength. It's not a part of every first order language. It's a part of every non-identity free first order language. There are people that study stuff without identities. Okay, we'll get to how you tell y equals x and whatnot. But oh, I see what your question was. Yeah. So it's not a false formula, right? It's just not a formula that makes sense right now, right? If I can, like, for example, if I if 1 and 2 were both equal to 0 and my signature was just 0, right, then this would be true. Okay. So our logical signature, by the way, is just the standard signature L, negation, and conjunction, and we don't, and this is functional complete, so we don't really care about we're not losing any generality, and we can define disjunction and implication and whatnot as before. Okay. And now we want to define the variables in a formula phi. We do this, of course, inductively. So var of s equals t is equal to the var of s union var t. Var rt1 through tn is the union of var ti, and var alpha and beta is equal to var alpha union var beta. Var negation of alpha is equal to the var of alpha, and var for all x alpha is equal to x union with the variables in alpha. No, I'm not an actual teacher. I mean, actually, I was. Not a good one, but I was. Okay. So let's take a look at a specific formula. Let's take a look at an interesting formula, which isn't obvious. So here, let's look at for all x, there exists y such that x plus y is equal to 0, and for all x, x is less than y. So here, for example, we have two variables, right? We have x and y. Let's take a look at all the occurrences of x and y. So this is our first occurrence of x. It exists within the scope of for all x. This makes sense, right? If I say for all x, there exists a y such that x plus y is equal to 0, that x sort of in a way makes sense. And then the y similarly also makes sense. But here, this x also, again, makes sense because it's within the scope of for all x. But this y doesn't make sense by itself, right? I can't just say that if I have a model, if I have a structure, so let's say n, the natural numbers, does the natural numbers satisfy this? Well, we don't know. What does y mean? What does y equal? So that brings us to the concept of a free variable. So this variable is called free because it's not within the scope of hi Ricey. It's not within the scope of a quantifier. I think that's probably more interesting than what I'm talking about, but unfortunately, I need to continue talking about this. Okay. Um, okay. So you want to define what a free variable is. So a free variable, obviously, we're going to define recursively. Um, so uh, so the free variables of phi we define recursively. So free of alpha is free of alpha is equal to the var of alpha for alpha prime slash atomic. Right, same thing. They both mean the same thing. Free of alpha and beta is equal to the free variables of alpha union the free variables of beta. And similarly, the free variables of the negation of alpha is equal to the free variables of alpha. And finally, the free variables of for all x alpha is equal to the free variables of alpha minus x. Right? Because once you quantify over x, all your free variables in alpha, all your x, the occurrences of x in alpha don't become bound. Right? The opposite of free is bound. So, right, these red occurrences of x are of variables are bound occurrences, and this is a free occurrence. Notice how because I don't remember how to spell occurrence off the top of my head, I didn't spell the whole word. That's a teacher trick. Okay, and I'm going to write phi is equal to phi of x bar to mean that phi is a formula, obviously, and the free variables of phi is a subset of x bar. Oh, yes, you can write existential quantifiers. Right, I forgot to mention that. So where do you want me to scroll up to? So quickly before actually I scroll up, we can define alpha disjunction with beta to equal the negation of alpha and negation of beta. Alpha implies beta to equal the negation of alpha and negation of beta, and the exists x alpha to equal the negation of for all x negation alpha. Yeah, so that's an important note that I should have. Oh, that should not be on. No, go away. Okay. And similarly, we write t is equal to tx bar to mean that the variables in t is a subset of x bar. Okay. And final definition. Well, not final. We have a lot of definitions. Don't worry. A formula, phi, is a sentence if it has no free variables. Okay, so now that we've defined the syntax of first order logic, we have to define the semantics of first order logic. We have to define what it means for a formula to be satisfied. So right before, it was very easy with propositional logic. We just took the evaluation and we extended it to all the formulas. Here, what we're going to do is we're going to take a first order model and we're going to find this relation recursively. Okay. Definition. Sorry. So an L model is a pair AW where A is a L structure and W is a valuation from variables to A. So it gives every variable a value in A. So that's what an L model is. And now we're going to use, so these are going to be denoted M usually. So we're going to denote R of A, F of A, C of A, and X of W, right, W of X, to be by R of M, F of M, C of M, and X of M, right? I can write, because M contains all this information, I don't need to write R of A, I can write R of M, because it contains A. Okay. Now, let M be an L model, and T an L term. We define the interpretation of T under M recursively. One, if T equals C or T equals X, T of M is already defined, right? Because we already have C of M and X of M, or M of X and M of C. And our compound terms are just going to be interpreted by F of M of T1 of M through Tn of M, or M of T1, whatever. So for example, let's say we have the model A, the real numbers. X gets mapped to pi, and Y gets mapped. Oh no, sorry, that's not a good example. X gets mapped to 1, and Y gets mapped to a half. Then X plus Y times Y, right? Let's say this is our term, right? T of xy, this gets mapped to 1 1/4, right? Because what we do is we plug in 1, we plug in a half times a half, so you get 1 plus a half times a half, and that gives you that. Okay. Now using this, we're going to define the satisfaction relation between formulas and models. So we write M satisfies phi if phi is true in M. So we have to define this recursively. So we start with atomic formulas. So M satisfies T equals S if and only if the interpretation of T is equal to the interpretation of S. This is where the equality being a primitive part of the language comes into play, because otherwise I couldn't have this. Like you could add it as a relation, but there's nothing requiring it to be the identity relation. This requires it to be the identity relation. M satisfies Rt1 through Tn if and only if Rm T1m Tnm. Right, this is a relation, so if and only if that relation is satisfied by these terms. M satisfies alpha and beta if and only if M satisfies alpha and M satisfies beta. M satisfies the negation of alpha if and only if M does not satisfy alpha. And finally, M satisfies for all x alpha if and only if MAX satisfies alpha, where MAX is equal to AW prime, where X w prime is equal to a, and yw prime is equal to yw. So the idea is m superscript a subscript x is just a model which takes m and replaces the valuation of x with a. Okay, so basically, so that's the satisfaction relation. We've defined it for all formulas. Okay. And also notice from this, right, because we defined it, we get for disjunctions that m satisfies alpha or beta if and only if m satisfies alpha or m satisfies beta. M satisfies there exists x alpha if and only if max. Oh, this is for all a in A. If and only if max satisfies alpha for some a in A, and so on. Okay. Just a quick little rundown of stuff that we've already seen before. One, phi in L or X. So a formula or a subset or a set of formulas is satisfiable if it has a model, right? I.e., some m which satisfies phi or x. Two, phi is a tautology if m satisfies phi for all models m. Three, alpha and beta are equivalent, right? Are logically equivalent if when m satisfies alpha, it satisfies alpha if and only if it satisfies beta. Four, so this one is a new one. So if A is an L structure, A satisfies phi if and only if M satisfies phi for all M which are models which are over A. 5. This is equivalent to basically taking if phi is equal to phi over x, A satisfies phi if and only if any model of M of A satisfies for all x phi. But doesn't really matter. You can convince yourself that that's true, or you can forget it. It doesn't really matter. Okay. If x is a set of formulas and phi is a formula, then phi is a consequence of x. If m satisfying x implies m satisfies phi. Right, the same thing as before, same thing as in propositional logic. Okay. Okay. Now here's a nice little theorem that this is the coincidence theorem. Okay. Let phi be a formula. B a set of variables between that contains free of phi and is so it's a set of variables which contains free of phi, and m prime models such that for all x in V, x of m is equal to x of m prime. Then m satisfies phi if and only if m satisfies phi prime. Yes, it will be. So basically what this says is that the satisfaction of a formula is based only on the variables which occur free in it. So the valuation, right? Yeah. So if I have, right, for all x, there exists y such that x is less than y, and I have a valuation m sorry, no, this is a bad example. Let's say I have the formula phi of xy, which is equal to x is less than y, and I have the model M, which maps x to 0 and y to 1, and z to 2, and I have the model M prime, which maps x to 0, y to 1, and z to 3, right? M satisfies phi if and only if M prime satisfies phi. Right, because this z here has no effect on the formula. And the proof of this it's not a trivial proof, but it's not a hard proof. And if you're interested in the proof, you can look at the lecture notes. I just think that you guys understand it intuitively. You shouldn't understand it intuitively enough for it not to matter if I show it or not. Now we're going to adopt the convention that if phi is equal to phi x bar, then A satisfies phi A if and only if M satisfies phi for M equals AW, where W maps X to A. Right, so basically what this means is that phi is true under A when we map X to A. And because of the coincidence theorem, it doesn't matter which model M we take that satisfies this, because if we take another M prime, which satisfies W with W prime, such that X bar is mapped to A, because of the coincidence theorem, since the free variables are both mapped to the same place, we get that one satisfies phi if and only if the other satisfies phi. And similarly, if t, we also have obviously we have the coincidence theorem for terms. So if t is equal to tx bar, then t a of A is equal to T of M, where M equals AW, where XW is equal to A. No, so what I'm saying here is that here I'm saying that I define this. Oh, in the theorem. Oh yes, M prime. Not phi prime. Yes, M prime models phi. Okay. So one example of this is if x does not occur free in phi, then for all x phi is equivalent to phi, which is equivalent to exists x phi. Now, why is this true? Because M a of x and M agree on free of phi, because x doesn't exist in free of phi. So by the coincidence theorem, we have this, which is called the mission of redundant quantifiers. Okay. Now here's an actual interesting theorem. Well, it's not that interesting. It's a lemma. It's called the substructure lemma. And what it says is that the following are equivalent. If A and B are L structures, with the domain of A being a subset of the domain of B, then the following are equivalent. 1, that A is a substructure of B. 2, that A satisfies phi A if it implies if and only if B satisfies phi A for all atomic phi and A in A. And 3, the same thing, but for quantifier free. So quantifier free formulas are just formulas that don't have any quantifiers in them. So the proof here, so basically what this means is that if I say x is less than y, right, this is a atomic formula, And A is if A satisfies this if and only if B satisfies this. Right, and this shouldn't be so surprising. It's just very nice to formalize. So let's prove 1 implies 2. So let M equal AW and M prime equal AW prime. No. And M prime equal BW. Then we show that M satisfies phi if and only if M prime satisfies phi. Right? This will be sufficient. Why is this sufficient? Because we're taking any model that we're taking any model that maps x to a, right? A here is arbitrary, so as long as both of these w's are the same, then it's fine. So if we show this, then it's sufficient. Okay, so so since T of M is equal to T of M prime, by coincidence, since T of M is equal to T of M prime, this is immediate, right? Because M satisfies T is equal to S if and only if Tm is equal to Sm, which is equal if and only if T of M prime is equal to S of M prime, which is if and only if M prime satisfies T equals S. And so on for relations as well. 2 implies 3. 2 implies 3. This is just because quantifier-free formulas. It's by formula induction. Formula induction without the universal quantifier. Okay. Now 3 implies 2 is trivial, right? Because 3 implies 2 is trivial because atomic formulas are quantifier free. And finally, we show 2 implies 1. Now 2 implies 1 is the most interesting, but that's just because here we define the formulas and then we get our result. So we know that Ra of A, if and only if A satisfies Rx bar with A, if and only if because we're assuming 2, and this is a prime formula, B satisfies Rx of A, which is if and only if Rb of A. Okay, so we get that we get what we need for relations. So right, this is exactly what we want to prove, that this if and only if this. And what we also want to prove is that f of A is equal to f of B of A, right? So we know that f of A is equal to B if and only if A satisfies f of x is equal to y, right? This I'll put in parentheses, A, B. If and only if, right, because this is prime, if and only if B satisfies f of x equals y, A, B. Which is if and only if fb of A is equal to B is equal to B. Yeah. So we get that f of A is equal to f of B, A. Which concludes the proof. Okay. Okay, so we can define a formula of the form for all x phi x, where phi x is for all x phi, where phi is quantifier free, is called universal. there exists x, phi, where phi is quantifier for me is called existential. I talk nonstop because I'm used to it. That's what I do all day. So this is a universal formula, and this is an existential formula. Okay. So for example, we can define the existential sentences. So exists one, which says there exists v1 such that v1 is equal to v1. And in general, exists n, which will be there exists v1 through there exists vn, the conjunction of 1, I, j, n, such that vi is distinct from vj. No, this is not the place. Sorry. And what this basically says is A satisfies exists n. Right? I can write this because exists n is a sentence, so I don't need to put the little a here, right? And I don't need to put for all in front of this. It's a sentence, so it has no free variables. Exists n if and only if A has n distinct elements. Obviously, at least. Okay, so this is a tautology. Exists one because we're going to assume that none of our structures are empty. So we can just define tautology to be equal to exists one, and contradiction to be equal to the negation of a tautology. And it doesn't really matter how you define it as long as it's a tautology, right? Okay. And we can also define, and exist 0 is defined to be the contradiction, which is just defined to be the inverse of that. The reason why this is called exist 0, it'll become understandable when you guys do the problem set. Okay. Okay. Unfortunately, we're coming to the end of the time, so I'm just going to say 2 more results and a definition, and then we'll be done. So a corollary is if A is a substructure of B, then every universal sentence true in B is valid in A, and 2, every existential sentence true in A is true in B. Right? Because if there exists something in A, then obviously that exists in B. And if everything is true in B, then everything is true in A because it's a substructure. So the proof of this is so B satisfies for all x phi x if and only if B satisfies phi A for all A in B, but this implies that B satisfies phi A for all A in A, and from what we just proved, that this is if and only if, right, A satisfies this. So that's if and only if, so or just implies A satisfies phi A for all A in A, which says that A satisfies for all x phi. And similar for 2. Okay, and our last theorem is as follows. It's the invariance theorem. And this tells us why we care about isomorphism so much. In my right, it sort of formalizes why we care. Let iota from A to B be an isomorphism, then for all formulas phi of x in L and A in A satisfies phi of A if and only if B satisfies phi of the iota of A. So what this says is that and in particular, if I have a sentence, if phi is a sentence, right, so it has no free variables, A satisfies phi if and only if B satisfies phi. So isomorphic structures satisfy the same sentences, and you have this very nice result that phi of A, that A satisfies phi with some valuation if and only if B satisfies phi with the isomorphism composed with that valuation. And what's very neat about this is it's not true just in first order logic. It's true in higher order logics as well. And that's because isomorphisms are just a very fundamental way of saying that two things are the same, pretty much. That one is a renaming of the other. And okay. The proof of this you can find in the lecture notes, which I will release soon after the lecture. And our final definition is A and B L structures are elementarily equivalent, denoted A is equivalent to B if for all phi in L, for all phi sentences in L, A satisfies phi if and only if B satisfies phi. Right? So as a direct result of the invariance theorem, we get that if A is isomorphic to B, A is elementarily equivalent to B. The other direction is not true. For example, and we'll prove this later, but R with the order is elementarily equivalent to Q with its linear order. But obviously they're not isomorphic because they have different cardinalities. So not isomorphic. Okay, so that's it. Unfortunately, there's a section that I was hoping that we'd get to that we didn't get to, because there's a lot of stuff to cover for first order logic to like build the foundations. But yeah, that's it for today. If there are any questions, I'm happy to answer them now. Of course. Thank you for coming. It was a lot of fun giving it. What's T1? This right now is undergraduate level, so like college level. second year maybe. Yeah, so that's a good point. Obviously, you need functions and constants when like what I said before about your signature, you're not getting everything. Like if you change your signature, you don't get the same results. So that holds true. But if you know enough about your structure, like you can like if you can prove um um you can define yes, but your formulas won't necessarily be true. Like I can say for every for there are theorems that are true for model for structures that have a constant in it that aren't true for theorems for structures that don't have constants. No, there's not an issue with circularity because we're not doing it. Like I said on the first lecture, we're not dealing with formalization here. We're trying to study math. We're not trying to formalize math. Um, Sharp gave a good answer to that, but we're not trying to like we're trying to study what we can extrapolate from math by sort of looking at the fundamentals of it, and we will talk about ZFC. Um, but there's no we're not trying to be like, oh, okay, this is exactly what a set is, this is exactly what a symbol is, this is exactly what everything means, um because that's just not the purpose. If that made sense, sorry if that wasn't the clearest. Let me Okay, if that's it, then bye. Thank you everyone for coming, especially Rice. um yeah, and I'll hopefully see you next week. Of course, my pleasure.